Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be solving more challenging modulus inequalities. So let's jump into the first example. We want to be able to sort of solve this inequality we're given, where we want the function f of x to be bigger than or equal to g of x, and we want to find all the values of x for which that's going to be true. And of course, the functions f and g are given, and they are indeed modulus functions, right? So I'm not going to talk too much about what the method for solving these things in general is. If that's what you're looking for, then please go back and take a look at the previous video. I'm just going to jump in and actually start to solve this. So we want to be able to get f of x and g of x, in fact, described in in the description of their branches. So in particular, I just want to be able to write f of x, and then I'm going to use the definition of the modulus function and then get those branches. So I know that the definition of the modulus function says I'm going to have x minus 3 for when x minus 3 is non-negative, and I'm actually going to have minus of x minus 3 when x minus 3 is indeed negative, okay? And of course, to that, given how f is defined, I've got to add 10 to it overall. So sort of just simplifying this, I know that that minus is going to go inside and apply to everything in that bracket, which means it's going to apply to each branch here. So I end up with minus x plus 3, and then I end up with just x minus 3, because obviously this minus would cancel with that minus. Tidying up the domains, I can say this part can just be x bigger than or equal to 3, and the other part can then be x strictly less than 3, and of course I'm still adding 10 to the overall thing here, so perhaps I should put the brackets here. So the way we would now simplify this is just go and just add 10 to the entire thing here, which means just add 10 to each branch here. So when I'm going to do 3 add 10, I'm just going to get 13. So we get this, and of course the domain is this. And then when I do minus 3 add 10, I'm just going to get 7. So we end up with this. And then the domain is, of course, this. So we now have a much more sensible description of f of x. We've got to repeat the same thing for g of x. So I'm going to say g of x is this thing here. And of course, by the definition of our modulus function, I'm again going to say it's going to be x minus 3 for when x minus 3 is actually non-negative, and minus of x minus 3 when x minus 3 is actually negative. So perhaps I should do that. And then we're going to add 2 to the overall thing this time. But obviously this still needs to be tidied up. So what I'm going to have is I'm going to have, doing the multiplication, I'm going to do 2 times by x, and then 2 times by minus 3 is going to give me minus 6. And 2 times by this entire thing in the bracket actually would give me minus 2x plus 6. And of course the respective domains will just be kept, but I can now just write it in a much more simpler way. And the overall brackets still apply, and that 2 is still there on the outside. So now adding that 2 to the entire modulus function, we just add it to each branch. So I'm going to end up with this thing here, which is going to be 2x minus 6 add 2 is minus 4, and that's all true for x being bigger than equals to 3. And then I'm going to have minus 2x, and then 6 add 2 is going to give me 8, and that's all true for x being less than 3. So we've managed to work out the description for f and the description for g in their branches. Let's make a bit more room and continue with this problem. So we end up with this. This is basically a rewriting of f and g, but really what we want to do is we want to be able to plot f and g because we're going to use the graphs of f and g to be able to solve our inequality for us in essence. But obviously we could now go away and just plot each one of these sort of straight lines and only keep them for each of these respective domains. But the easier way of doing this, I tend to find, is actually thinking about transformations, right? So I can get the entire function f of x here by basically doing this transformation here, by starting with modulus of x and then doing modulus of x minus 3 and then taking the negative of that and then adding 10. And similarly, we can get the entire function g by actually starting with modulus of x and doing this transformation here. So let's see what this would actually look like. So indeed, what this would look like is we would start with modulus of x, and then we would actually go to sort of modulus of x minus 3. So if I take my f of x to be modulus of x, right, then we can see that the first part here it's just going to shift everything to the right by 3, and that's basically this thing here. And then we want to put a negative in front, which means we're going to actually have a reflection about the x-axis, right? So now I've got all of this thing here essentially, and then we're going to want to add 10. That's the same thing as shifting it vertically upwards by 10, right? And we can repeat the same sort of analysis for this. And of course, we can sort of look at the big picture, which is shift 3 to the right, and then stretch by 2 on the y-axis, and then shift by 2 vertically upwards. And once we go and perform both of these sets of transformations, we actually end up with these graphs. Okay, so that's quite nice. We see that this orange one is actually the graph of G, and that makes sense because it's sort of facing upwards essentially. It's just been shifted up, whereas the other one actually has a negative, which means at some stage this purple graph was sort of up here, and then it got reflected down, and that's why it's sort of facing this way, and then it just got shifted to this sort of location. Anyway, so we want to actually solve for that point there. And to be able to solve for that, we need this branch and we need this branch. So we need to know what these branches are, which is why we actually did this sort of thing earlier, right? So we know this is g of x, and we know this is the branch with a positive gradient. So that basically has to be 2x minus 4. And then the other one, we know this is f of x, and we know this is the branch with a negative gradient, and that has to be this one. And it's reassuring that this is valid for x being bigger than 3. So we see that's actually, yeah, that's consistent. So this is going to be minus x plus 13. So we solve these two simultaneously. So let's do that. We're going to have 2x minus 4 is equal to minus x plus 13, which then obviously we sort of rearrange, and the left hand side just becomes 3x and the right hand side just becomes 17. So x actually turns out to be 17 over 3, which means if I actually come down from here, I'm going to get something like 17 over 3. Okay, so let's now go away and work out what this point here is going to be. But of course, to be able to work that point out, I need this branch and I need the other branch. The first branch is g of x with the negative part, so it's going to be this. It's going to be minus 2x plus 8. And the other one is going to be f of x with the positive branch. So if I go to f of x and if I look at the positive branch, which is this, which is valid for x less than 3, and that makes sense. So it's just going to be x plus 7 here. So let's now solve these together simultaneously. So we're going to have minus 2x plus 8 is actually equal to x plus 7. And rearranging this, I take the negative 2x to the right-hand side. That just gives me 3x. And I take the 7 to the left-hand side. So the 8 minus 7 is just going to give me 1. And that just tells me that x actually is equal to a third. And that's again reassuring because I actually get a positive solution here. Okay, so I actually get a third. So let's now take a look. We want f of x to actually be bigger than equal to g of x. Well, our f of x is this sort of purple graph here, and we want it to be bigger than the orange graph here, and we see that's only really true in this sort of region here, right? For this entire region here, if I, for example, take a vertical line, and if I just compare what's happening here, I see each point on the vertical line, the purple part of the graph is actually higher than the orange part of the graph, and only at that green point and at that red point are the two sort of purple and orange graphs equal, and then on the other side we have the orange winning compared to the purple. So the solution is indeed just going to be in this sort of region here, so let's just write that down. So we're going to say solution is going to be x is bigger than equal to a third and less than equal to 17 over 3. And of course, it is also conventional to actually mark that sort of on diagrams in this sort of way. Okay, and in this case, we are going to include a third, and we're going to include 17 over 3 because our inequality is actually soft. So that completes the first example. Let's go take a look at the next example. Example 2 is a very interesting example. Here we have another modulus inequality, and of course this is a little bit harder perhaps than the previous example, largely because this modulus function here is a little bit more involved, okay? We still want to find all the values of x for which this inequality is satisfied, so let's actually just jump in and take a look at a solution. So what I'm going to actually do is I'm going to define that modulus function as f of x. So let me perhaps write that out. So it's going to be 2x plus 1 modulus, and it's going to be 2x minus 1 modulus. And the idea here is, well, if I can get a handle on what f of x actually is, then it's not going to be that bad or that hard to figure out when f of x is going to be more than 5, right? But how am I going to get a handle on f of x? Well, you can do a few things. You can just use transformations to be able to graph this, and that's one way of understanding it. But really, I think a slightly better way of understanding it is at least to see what the branch description of f of x is going to look like. So let's do that. So let's expand that in a branch and then expand that in a branch and then combine them. So 2x plus 1 modulus, by the definition of the modulus function, is going to give me 2x plus 1. And of course, that's only true for 2x plus 1 being non-negative. And then the second branch is going to be 2x plus 1, but all of it is negative. And that's when 2x plus 1 is indeed entirely negative. So that's the first modulus function. The second modulus function is going to be, by the same definition, it's just going to give me this. And indeed, it's just going to give me that. So we should be very, very comfortable with this sort of thing now. This is just something we've seen lots of times in lots of videos now. So, so now here's the slightly hard part, which is how do I now start to combine these things, right? And the slightly tricky thing is, well, actually, what I'm going to have to do is I'm going to have to figure out what's happening with these domains here, right? So let me first of all rewrite all of this in a slightly more simplified version so I can make heads or tails of the domain sort of more sensibly. So I'm going to say 2x plus 1, and obviously the domain is going to be the same thing as x bigger than equals to a half, and then expanding this negative in, I'm going to get minus 2x minus 1, and the domain respectively for that is going to be x less than a half. And I repeat the exact same thing for the right hand side, which is going to be 2x minus 1 for the domain being x bigger than equal to a half, and minus 2x plus 1 for x being less than a half. So this is slightly better. Let's now think about sort of a straight line, right? I say straight line, really what I mean is the real number line, and I want to mark sort of special points on here, and the special points actually are, indeed, as I do this, I realize this should actually be a negative here, and so should that, and then the other one should actually be a positive. So perhaps let me tidy this up. Okay, that's slightly better. So let's mark our key points, which is a half and minus a half. There are 2 points because we have minus a half being the relevant sort of point coming from that chunk of the domain, and then a half coming from here, which is obviously a restatement of these inequalities. Okay, so what's going to happen when we actually have x being bigger than a half? So when x is bigger than a half, so indeed that sort of region there, that's definitely going to apply because that's where x is bigger than a half, but also that's going to apply. So I'm just going to combine that with that. So let's write that down, which is 2x plus 1 plus 2x minus 1. And of course, this is true for x bigger than equal to a half. So maybe I can color code this as follows. So I can say that part's going to apply and that part's going to apply on all of that region here. Okay, good. So now let's look at the region which is between half and minus a half. So let's say that here. Okay, so what's going to apply? So it's going to be bigger than minus a half, which means that part is going to apply. And it's actually going to be less than a half, which means that part is going to apply. Okay, so let's put those together. So we're going to have 2x plus 1, and we're going to have add minus 2x plus 1. And of course, this add here is basically that add there, and then the minus 2x plus 1 is this thing here, and then the 2x plus 1 is just this thing here. So we can say that that's completely fine. And lastly, let's look at the third chunk, which is everything where x is less than a half. Well, that's completely fine. I should say x is less than minus a half. That's completely fine, which is here, everything is less than minus a half, or indeed here, which is because if x is less than minus a half, then it's necessarily less than a half. Okay, so now I just add that to that. So let's see that in action. So I'm going to get minus 2x minus 1, and then I'm going to add minus 2x plus 1. Okay, so I should have actually written these domains down like so and like so. Indeed, being mindful, I need to worry a little bit about whether these are going to be hard or soft inequalities. Okay, so I can see actually, given that this is describing the green region here, and the green region is made up of this branch and this branch, I see that there is a soft inequality there and a hard inequality there. So in fact, what I'm going to have is I'm actually going to have a soft inequality here and a hard inequality for the other thing. So we really do need to now just simplify this, and this is very easy because we see what's going to happen here is the 1 and the minus 1 are going to cancel. So we're just going to get 4x here. And here, the 2x and the minus 2x are going to cancel, so we're just going to get a 2 overall. And for the bottom branch, we're just going to get minus 1 and 1 are going to cancel, so we're going to get minus 2x to actually give us minus 4x, right? So let's see what this looks like. So here we have it. This is the description of our function f of x now in a much more sort of nice way. And we have our respective domains. And indeed, we actually have a graph of f of x here. So we see what this looks like. And in fact, these two red graphs are, each of these are sort of graphs of our branches. So we have something like this, and we actually have something like that. Okay, so that's the one of them, and then that's the other one. And we see actually, since f of x is indeed 2x plus 1 modulus plus modulus of 2x minus 1, then actually we're getting the green graph by basically adding up the red graphs, okay? Consider that point there, right? So how do we get that point there? Well, we got that point there by adding, if effectively, sort of, if we come to this point here and this point here, right? So we took that height there, and we added it to, if I actually just come to the side to make it more visual, we added it to that height there. And when we sort of add the small height to the slightly larger height, what we find is we end up with a height which is sort of this tall, right? So let me maybe sort of do it in green. So we end up with this height here. So indeed what I'm saying is that blue chunk there is exactly the gap between here and here, right? And you can go and repeat that for each point on a sort of green curve, and you'll find that this perfectly works, right? So this is a geometric way of understanding how to get the green curve from those two red curves. Anyway, so let's go back to the problem that we were actually working on. So we actually wanted to solve f of x being strictly bigger than 5, if I recall, right? So you can see we have y equals 5, which is a horizontal line, and we see for sort of this part of the green curve, it's actually higher than the horizontal line. And similarly for that part of our curve f of x, this thing here is actually lower, right? So we basically want to figure out that point there, and we also want to figure out this point here. So let's maybe mark them 1 and 2. So let's call the first one 1 and the second one 2. So we solve the first one by basically solving simultaneously this right side of our f of x function with y equals 5, right? But we know what the equation of this is because we have our branch, okay? So we know it's going to be 4x being equals to 5. So let's do that. So 4x equals 5, which of course tells me x is nothing other than 5 over 4, so that's pretty good. And then for point 2, we do the exact same thing, but now we have a different branch. We actually have this branch here, right? And that's basically nothing other than minus 4x, right? And we want that to be equal to 5 again. So we're going to say minus 4x equals to 5, and that basically tells us that x actually is equal to minus 5 over 4. So we've managed to figure out basically what, if I come down, this is getting a bit messy now, we've managed to figure out that this point there is going to be 5 over 4, and the corresponding point on the left is actually going to be, again, let me mark it, minus 5 over 4. So visually, we can just know that actually our solution is going to be this entire region here and this entire region here. And of course, these points are not included in themselves because of the inequality being hard. So let's just write down our solution. So we're going to say solution is x is either less than minus 5 over 4, or x is actually bigger than 5 over 4. Okay, so I hope you found this useful. Let's take a look at the next example. So example 3, this is actually the last example of this video, but this example is split up into 3 parts, okay? So what we're going to do is we're going to revisit the slightly tricky modulus function that we had in the previous example. And what we're going to do is we're going to look at modulus inequalities, which are actually a little bit more complicated than the one we looked at in example 2. So in particular, in example 2, we had f of x being bigger than 5, but now we want solutions for f of x being bigger than minus 2, the modulus of x minus 1 in this case, right? The nice thing about doing this example is that we've already spent a lot of time thinking about this modulus function, right? So here's the graph of this, which we actually figured out in the previous example. And then the graph of this modulus function on the right-hand side is actually just here. That's not that tricky, right? This is the sort of thing we should be comfortable with. And in fact, if we now want to solve this inequality, we can just do that just by looking at this, okay? Because we see that actually the green graph is always above the blue graph, right? And the green graph is our f of x, and the blue graph is our other modulus function, and we precisely wanted to solve the inequality for when the green graph was actually going to be higher than the blue graph, right? So we know what the solution here is. The solution here is for all x being real numbers, the inequality f of x actually being bigger than is actually satisfied. Okay, so just a quick remark before moving on to sort of part 2 of this example, which is we could have actually written the solution down for this without even doing any of this in the first place. The reason for it is just by looking at this description, we know that this thing here is always going to be positive, and we know that this thing here is always going to be positive because these are modulus functions, right? So when we combine them, the overall thing is always going to be positive, and of course the graph just tells us that directly. But if we look at this function here, so I agree that this part here is always going to be positive, but it's being multiplied by minus 2, which means this overall thing here is always going to be negative. So you've got something that's always positive and something that's always negative. So we know that this is going to be true for pretty much any x value you pick. Okay, so good. Let's try part 2. So now we have the exact same function, f of x, so perhaps I should actually say this. I should say f of x is this thing here, and now we have a slightly different function here, right? So from part 1, what we actually have here is the old sort of blue curve has now been shifted up by 2, okay? So we see that this is now the state of affairs graphically, and we still have to solve for all the x values for which the green curve is going to be higher than the blue curve. And the solution in this case is also going to be quite interesting because some of you might look at this and think, well, you know, there is this point here where somehow the green curve and the blue curve are actually equal to one another. And that would actually be a misconception. That would be a misunderstanding of the concepts at play here, because you've got to really compare these things using a vertical line. Okay, so let's think about this. So let's think carefully. So if I was to slide this vertical line here, now compare the intersection of that green curve compared to that blue curve, which is higher, right? The green curve is clearly higher, okay? And if I keep that up, actually the green curve is always going to be higher. So even at that point there now, right, I can clearly see that my green curve intersects there, but my blue curve intersects there. So the intersection with the green curve is actually higher. But if I was to carry this on and actually come to the point at which we had this sort of possible issue of there being an equality, there isn't an equality. For this x value as input, this blue modulus function gives me y equals 2 as output, but the green modulus function gives me a much higher output. So in fact, for this input, I'm going to have f of x being definitely bigger than this thing on the right hand side. Okay, so this inequality will actually be satisfied there too. And indeed, for all the rest of the other points, the same sort of holds true. So in fact, what we see is the solution is still every single x value's input, right? So the solution is inequality holds for all x being real numbers as inputs. Okay, great. So let's take a look at part 3. Now, part 3 is where things actually get a lot more interesting. We, of course, have the same f of x function, but we don't have the same blue function. What we've done is we've actually now shifted the blue function up by 10 from the function we started with in part 1 of this example. And now we clearly see there are intersections. And now we clearly see that indeed there are parts where the green function is still higher, the graph of the green function is still higher than the blue function, but there is a region where the graph of the blue function is actually higher than the graph of the green function. Okay, so we need to figure out the x value at this point and the x value at that point. So let's maybe mark these as put the points 1 and points 2, and of course we need to know what sort of these branches are going to be, right, respectively, and we can sort of work that out. Well, for f of x, we did all the hard work in sort of the previous example, example 2, so we know that it's going to basically be like this, and we also know that the domains are actually going to be like this, right? So it's going to be that, the domain is going to be bigger than minus a half, but strictly less than a half, and the last one is going to be x being less than minus a half, okay? So that's completely fine. So the one that's slightly harder work actually is going to be this function here. Let's call it g of x. And what we're going to need to do is we're going to need to express g of x in its branches, right? So maybe I can sort of do a bit of work here. So we're going to have g of x, and we're going to have that's the same as minus 2 times by, I'm going to expand the modulus function to give me x minus 1, and that's going to be true for x being bigger than or equal to 1, and minus of x minus 1, and that's going to be true for x being less than 1. And then we're going to add 10 onto the entire thing, which if I simplify, I take the minus 2 on the inside of my branch, I'm going to get minus 2x plus 2, and then I take the other minus 2 again into the second branch, I'm going to get 2x minus 2, right? And of course, the domains are still going to be what they were. And then I need to add 10 to this thing overall, which actually gives me minus 2x plus 12 and 2x plus 8 respectively, and the domains, as I keep saying, are not going to be impacted by it. So now we have a description for G in branches. We're now much closer to being able to solve this problem, right? So let's just make sure the graphs we've worked out actually pass the sanity check, right? So this branch here has a negative gradient, and that's describing my g of x, and it's describing this part of my g of x, and it sort of stands to reason that that point there is going to be 1, or the x value at that point there is going to be 1, so all of this chunk here is being described by that thing there. So let's just mark that. So this thing here is going to be minus 2x plus 12, which means the other thing here has to be 2x plus 8. And this is reassuring because that looks like it's going to be about 8. It's between 10 and 5, and it's slightly closer to 10 than it is to 5, right? And of course, if I was to sort of extrapolate this, then this would have crossed at the top sort of 12, and that's consistent with what we've got here. Right, so what we can now do is we can solve for 1, and we solve for 1 by basically setting 4x equals to this part here. So I'm going to say 4x is actually equals to minus 2x plus 12, which tells me that 6x is actually 12, which actually tells me x equals 2, so that's pretty good. And then we're going to solve for the second point, or the x value of the second point, by setting this branch here, which is obviously just minus 4x, to sort of this branch here, which is 2x plus 8. So I'm going to say minus 4x is actually equals to 2x plus 8, which is nothing other than, if I actually sort of take that to the left-hand side, it's going to give me minus 6x. So it's going to give me minus 6x is equal to 8, which actually tells me x is actually equals to minus 8 over 6, which of course we can simplify to say minus 4/3, right? So we've managed to figure out that actually if I come down here, then this thing here, apologies for the sort of wavy line, it should have been a straight line. This thing here is going to be 2, and if I come down here, then this thing here is actually going to be minus 4/3, right? So now we want f of x to basically be bigger than this thing here, which is g of x, which means we're interested in that chunk there, and we're actually interested in that chunk there. Okay, so let's mark that explicitly. So we're going to want this part here, and we're going to want this part here. And again, because we're dealing with a hard inequality, we're not going to count that in, and we're not going to count that in. So I can perhaps just write down the solution. I can say solution is x is less than minus 4/3, or x is actually bigger than 2. Right. So I think that's a good place to end this video. I do hope you found this really useful. If you did, please do hit the like and subscribe buttons. As always, please let us know in the comment section as to what you would like to see more videos on. Thank you for watching this video, and we will see you in the next video.